Okay, so good afternoon. We will end today the lecture on special relativity. Let me see if I can. Okay, so let's begin this one. So last time, today we will finish this topic. Relativity, special relativity. Let me go straight to the point. Okay, so what we saw in the relativity. Well, yes, I know. I remember. We were studying the Michelson interferometer. Okay, so I won't go back to the Michelson interferometer because really we don't have much time. Just let me remember, okay, what it was about. Okay, the Michelson experiment was meant to measure the velocity of the Earth relative to the ether. Okay, this medium, okay, material medium where electromagnetic waves propagate. Okay, so the result of this, it was a very, very sensitive method. Let me see here if I still have the slides. Yes, here. Okay, so it was a very sensitive method. Okay, you have it consisted in interfering two light beams, the two beams coming from the same original beam, okay, and they are dephased because they should have a velocity in the direction of, on this direction, which is the direction of this leg, okay, here, this path in relation to the ether, and this one is perpendicular, so the velocity, propagation velocity should be different. So when you recombine the two beams here, you should see some dephasing, and so you can put, this one, you put this this mirror slightly tilted, and so you will have not a point, okay, but you will see an interference fringes, and so you can measure the distance these fringes will move. For example, when you rotate the Michelson interferometer, okay, because it should change, because the path which was in the first part parallel to the relative velocity will now be perpendicular, and so on. So it is a very, very, very sensitive experiment. Here there are some details. Okay, I wrote it here, okay, path 1, path 2. I won't go into the details here, because what is important here, you have to have very big paths, okay? The distance between, okay, this distance here and this distance here were of 11 meters. It's very big. The wavelength was yellow light at 600 nanometers. And so when you calculate the fringes shift, and you know what is the relative velocity of Earth, okay, moving around the sun at around 30 kilometers per second, and you know the distance between Earth and Sun, etc. So you should have something like 0.4 of a fringe, okay, almost half fringe. It's it's very big, okay? It's huge. And so they should have seen it. They had actually a sensibility. They could measure 10 to the minus 2, okay? And they were expecting 0.4. So they didn't measure anything. So until now, until up to date, there are some experiments, okay? Meant to measure. I think everybody now is convinced there is no such medium for electromagnetic wave propagation. But even today, you do this experiment. Obviously, it doesn't exist, so you do the experiment. It can be as precise as you can, as you want. You won't measure anything, okay? And so, what is the result of this? There is no privilege medium, okay? There is no privilege frame of reference, okay? In which the Maxwell's equations, you do remember the wave equation? Maxwell wave equation is here, okay? So you have this equation when it's Maxwell, okay? This is C here, the light, propagation speed of light. And so which reference frame is that? It seems there is no preferred, there is no privilege, there is no singular reference frame where the velocity of light is c. This is very strange, okay? And so Einstein solved, okay, the problem. He said two things. Postulate one, the laws of physics are the same in all inertial reference frames, okay? We studied last time this, okay, relativity, the law of relativity, classical relativity, which is the laws of physics are the same in all inertial reference frames. And if you have one reference frame, what is a reference frame? It is what is an inertial reference frame? It is a frame where the law of inertia, the first law of Newton, holds, okay? It is valid. So if you don't apply any force on the particle, okay, it will have a constant velocity, vectorial velocity, okay? And if you have one inertial frame, if there is another, okay, reference frame, which has a constant velocity in relation to the first one, so this one also will be an inertial reference frame. And in these two frames, you can apply the laws of Newton, for example. And also, it seems, okay, and Einstein is saying also Maxwell's, okay, laws. And so, the second postulate, okay, so we saw there is a problem because normally when you pass from one reference frame to the other one, you should have the velocity is different, okay? And so it has been proven that light has no specific, okay, has no privileged reference frame. So second postulate, the speed of light in a vacuum is equal to the value c independent of the motion of the source, okay? And so this is the new thing, okay, that Einstein said. So it doesn't demonstrate it, it just says it, okay? So a postulate is this. You say something, okay, you say, well, I say this, and you will build a theory, okay, on top of these postulates. And as long as the theory holds, as long as it is valid, as long as you don't experimentally demonstrate it is wrong, okay, it is true, okay? So until today, it seems this is true, okay? So these are the two postulates that Einstein used to build his.
Martine.
Yes.
I didn't understand how the the wave's dephasation implies that the inexistence of the ether, of a
Okay, the Michelson
privileged
experiment.
referential frame.
Yes, okay. So maybe, okay, we are here. Let's take our time to explain it. Okay, so you have the experiment. Are you seeing the Michelson interferometer here?
Yes.
Yes. So you have this path, okay, which is perpendicular to this one, and it is aligned. This one, the path 1, okay, mirror 1, mirror 2. Path 1 is aligned with okay, ether. I don't know exactly how you pronounce it, but ether is this medium, okay, you are looking for, actually. And so in this direction, you should have a velocity, okay, of light, which is different. We will see here. Why? Why will it be different? Because the velocity of light in this frame, reference frame, is c, okay? But in the Earth frame, it is different, okay? Because, why is it different? Because Earth is moving relative to the ether. You understand? So it's the
Okay.
same thing as what you know. And in this second path, path 2, you don't have, okay, this difference because it is perpendicular to the relative velocity, okay? So you measure here expressions T1, okay, the time, okay, light takes to do it, going back, up. And so you have to, okay, this is this, okay? Here you have on path 1, you have this one. Light, when it goes this way, okay, Earth, ether is going this way, so it is slower. Light should be slower, okay, in the reference, okay, and it should be faster in this one. So you have a difference of time. It doesn't take the same time to go and to go back. Here it takes the same time to go and to go back, okay? So you calculate this time, okay, to go minus to go back, plus, okay, sorry. Okay, and we introduce here, it will be important, okay, this new coefficient beta, which measures u. I will use u, okay, which is the speed of s. Actually, this is Earth relating to ether. Okay, here it's an old. Okay, u is the relative velocity of the two reference frames. Okay, and in this direction here, you will have this construction. Okay, so it is c prime, and this is this velocity. Okay, so you calculate the time, okay, t1, t2, and so you should have some optical path difference, okay? And so you calculate this difference, and if you rotate it 90 degrees, so you already can measure it, but actually you will see the difference when you rotate your frame, and you will double. You can calculate, okay, and you will see the total shift, okay, here, the second, okay, when you rotate it, this is the first, so the shift, okay, should be this one. You calculate D equal 11 meters, beta, which is U over C. I said this was 30 kilometers per second. Okay, you know it. Okay, 1 year to go, blah, blah, blah. Agents, you know the velocity of the Earth. This is an approximation, of course, and so you find it. This is only this. The fact you are saying is if this ether exists, okay, there will be a difference between the time, okay, these two times. And you can measure it with interferometry. Did I answer your question?
Yes.
Yes.
Thank you.
Okay, so this is very important, and now we are going to use a lot of trains. I like trains. Okay, so you have special how do you say it, ships. Okay, but I will do it with train. Train is not very relativistic, but it's only a thought experiment. Okay, so we will see the first thing that the simultaneity is relative. Okay, so we are used to, you remember when you describe something, okay, a movement in one reference frame or in another, you can have some transformation, spatial transformation, x, y, x prime, y prime, z prime, and velocity also, but the time is the same, okay? And so what we are going to see if you believe these two postulates, okay, well, if you want to really apply them, you have to change something. And so what you will have to change is the notion of time, okay? And so the first thing is simultaneity is relative. So what is simultaneity, okay? And on the definition is, you have to be very precise. If an event 1 takes place at position P1 at time T1, and is accompanied by the emission of a light signal, okay, at the time T1, and the same for an event 2, okay, other position over time, then these two events are said to be simultaneous if an observer at point O half, okay, the distance between P1 and P2, okay, if an observer detects the two signals at the same time, okay? It seems very logical, okay? So you are at the middle, in the middle of the two position, and you will detect the two signals. Light signal, why are we going to use light signal? Because this is our reference now. It has the velocity c in all directions, in all reference frames, okay? So when event 1 occurs at P1, okay, when event 2 occur at P2, they emit a light signal, and you are right in the middle, and you will receive these two signals at the same time. So you can say that these two events were simultaneous, okay? Sounds right, okay? So let's see here. You have a train, okay? So this is the platform where you are looking, okay, at the train. The train has a velocity v. Well, I use the figures of the books, and it is not necessarily my notation. I like to use u, okay? But this v is the velocity of this reference frame S prime in S, which is the reference frame of the platform, okay? So there is no fixed reference frames, okay? You have to say, if you are an observer, okay, you are here on the platform, you say, this is the reference frame when where you are, okay, at rest, okay? And so this is another one, S prime, going at a velocity v in relation to S, okay? And so you have 3 points here. You have A, B, and C. And so what happens? You have some thunder, you know? And so you will have two things. It's important because you will have a mark, okay, at the place where the how do you say, the light rays strikes, you know? So you will have a mark, and you will have some light signal, okay? And so if you look here, and you have an observer between the two, okay, points here on the platform, and the two marks, okay? You have one mark here, one mark here, okay? So this observer C is right in the middle, and this C prime is also right in the middle. This one, okay, having a velocity V. So what happens? The mark is here and here, okay? So, and it is here and here. So when the signal, the mark was made here, there was emission of a signal, okay? And so this is the wavefront, okay, of your light, and it is traveling at velocity c, okay? And this is the wavefront of the second signal, and it is traveling at the same velocity c, okay? And so this observer will receive the two signals at the same time, okay? Because they were emitted in his reference frame at the same time, and he will receive the light signals at the same time. So he will say, okay, these two events here and here were simultaneous. Okay, now what happens with observer C prime? As the train, okay, is traveling with a velocity v, so light, okay, this observer will receive the signal emitted from A before the signal emitted from B. So he will say these two events were not simultaneous. Does it make sense?
Yes.
Okay, so this is very simple. So there is, in this sense, this is not a revolution. It is only, okay, you have to change, okay. Actually, time is not the same. Well, we are seeing the relativity of simultaneity, but it will lead us to the relativity of time. So time depends on the reference frame, okay? And so, okay, someone asks question? We will apply it in some problems and exercises, so you will see it's not that... it's only this notion. It's not a problem, okay? It's true, okay? You can write it, and we will write it formally, okay? Quantitatively. And so we are going to see now the Lorentz transformation. So you have a frame, okay? You have to define very precisely what is your frame to describe events, okay? So you have the position, as we say, you have event 1 occurred at position 1 and time t1, okay? Position p1, time. So how do you measure, okay? You always have to think in terms of measurements, okay? So how do you know, okay? You have no problem with your clock or with your space, okay? Because it seems quite a problem. So let's say on the platform, you can take some rule, and you can, okay, put some 1 meter, 2 meters, 3 meters, okay? And so at each point here, this is what is drawn here. You have 3D, okay? So it's beautiful, but it's not very clear. So we can do it in 2 dimensions as well, but this is a 3D diagram. And at each, okay, so for example, you have between this one and this one, let's say we have 1 meter, okay? So at each mark, okay, you put 1 clock, okay? So you have, your frame is full of marks, okay, saying this is the position, okay, and also full of clocks, okay. At each point you have a clock, and you have a position X, Y, Z, okay. And so the problem is, how do you synchronize your clocks, okay? So you will. It's very easy because you have the second postulate of Einstein, okay? So you know the distance between the 2 clocks, okay? And so you will send some for example, this is, where is the origin? I don't know if we can see it. Let's say this is the origin of my reference frame. And so you will put clocks, okay, a series of clocks, and you will send, at some time, you will say, this is time 0 for me. You will send some signal, okay, light signal. And so it will take some time to reach this clock, okay? But when it will reach it, you know the distance and you know the speed of light. So you know what time it is. So you put this clock at the time you know it is. Do you understand? So for example, it takes, I won't use 1 meter because it's very small. Let's say, okay. Let's say it takes 1 second. Okay, let's say. Light takes 1 second to go from this clock to this one, okay, to this position, to this position. So when at time t equals 0, I said this is t equals 0 and emitted a light signal, okay. So it took 1 second for the light to reach this clock, okay. And so when light reaches this clock, you can put this clock, it's 1 second, okay, and so on, 2 seconds, 3 seconds. And so you can do it, and you can have a 3D array of synchronized clocks. It's very important to have synchronized clock, because when you will measure the time of events, okay, you have to measure the time, okay, with the clock which is at the place of the event. Okay?
Okay.
Seems ridiculous, because the velocities we are used to are so small, but when you are with velocity close to light speed, okay, it begins to be very important, as we will see. Okay? So it explains here, when wavefront reaches clock I, okay, so you know that the time at this clock begins at this time, okay, because you know the distance and you know the velocity. Whatever, okay, your reference frame, the velocity of light is c. This is very convenient, okay. And so let's see now the Lorentz transformation, okay. So if you remember, the Galilean transformation is this one. You have two reference frames, S and S prime, and you have S prime traveling at a velocity along the x-axis, okay, at speed u, okay. And so in the Galilean transformation of coordinates, we can write that x prime, okay, you have some point here, okay, and so you can have here it's x prime, and here it's x, okay. And how do you measure the distance in one referential and in the other one, okay? At time t equals 0, t prime equals 0, and the two origins of the referentials are the same, okay? So from this you can write, we already did it, okay? You know it very well. X prime equal x minus ut, and x equal x prime plus ut prime, okay? And so now we are going to, what is the thing? The thing is this one, okay? We suspect it's not completely true, yes? So we will have to take it into account. And so what we can do is we can say that x prime, we can express x prime as a function of x and in t, okay? Simply by multiplying by a coefficient we will call gamma, such that when beta, what is this? Do you remember? Beta is u over c, okay? So it is always less or equal to 1, okay? And the only way beta is 1 is when it is the light propagating. You have c over c is 1. Otherwise, u is always smaller than 1. Okay? And so we say it should be proportional, okay? It should be a linear transformation, okay? And the other thing that will help us change, okay, this find actually this coefficient is the following. You should have x, okay? You should have the same transformation, okay? And so you write it x equal gamma x prime. What is x prime? It is gamma x minus ut plus, okay? And so you write it, and you end up with this, an equation that you solve in, I think you have to, it's not sufficient, okay? The other thing here, okay, it can be an exercise to find what this coefficient gamma is, but you can write also that if you have, okay, so you have one equation here, okay, and here you have another one, which is let a flash of light start from the origin of S at t equals 0, okay? So this is a very strange experiment because since we have assumed that the origin coincides at, okay, at t equals t prime equals 0, the flash also starts at the origin, okay? So at S prime, t prime equals 0, you also have a flash which will expand, okay? And the thing is that in both reference frame, the light will propagate at velocity c. So you will have in each referential, you will have the wavefront, okay? That will be a sphere, okay? It is a spherical wave, okay? And it is expanding, okay? And the distance, okay? If you want, the radius of this sphere is ct or ct prime, okay? Depending on the referential. The velocity is the same. It's very strange, okay? And so you write that this is, or what is it? This is the radius r square of this wave, spherical wave, okay? And it is, okay, you have, I said, it's 3D, okay? So if I put here y, x, and z is here, for example, and so you will have, this is r, okay, r equal to ct. You agree? This is the speed of propagation and the time in reference frame S, okay? And so you also know that the equation, okay, of the surface, okay, here actually you will have r square, x square, okay? Okay, okay. So you write this one is equal to this one. And so to have, you should have the same thing in the other referential, okay? X prime, Y prime, prime. And so with these two equations, okay? And so blah, 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 what you will find, you will solve the system in gamma, and you will find that gamma is a coefficient that depends on the velocity, the relative velocity of the two frames, okay? And so you can apply it. This is called the Lorentz transformation of space-time coordinates. We don't have space coordinate anymore. We have space-time because time is part, okay? This is the fourth dimension. And so you have, I wrote here, here you pass from x, no, from S to, okay, the position and time in S to position in and time in S prime. X prime, okay. These are equal because they are perpendicular to the relative movement. And T prime, okay, you can see, you can show that it has this expression. Oh, look, this is very interesting, okay. You have the time as measured in reference, okay, frame S prime is different, okay. It is a function, okay? But it depends on the relative velocity of the two frames, okay? So this is really, really new, okay? And so you can do the same, passing from S prime to S, okay? X, blah, blah, blah. All you have to do is invert, okay? This is a relative movement, okay? S prime is passing at velocity v here, or u, in relation to S. This is the same as saying that S is passing with relative velocity minus u in relation to S prime, okay? So this is the Lorentz transformation of space-time coordinate. You pass from, okay, this here to this one. Okay. And so, I don't know if I will do it later, okay? So this is some kind of, this is an example. It's very simple, okay? We will use a lot of cosmic rays. You have particles, okay, which are decaying, for example. So they don't live a lot of time, okay? And this one is a cosmic ray. It's a mu meson, okay? So it's some kind of particle. And they are coming from, okay, they are cosmic rays, okay, in the cosmos. And they are recorded by detectors in the laboratory, okay, in the laboratory. And so if I call S this laboratory, this is where I'm at rest. This is where my detector is at rest, okay? And this particle is has a very, very high velocity, okay? In relation to this one. So you have your mu particle, so you can attach a tiny, okay, referential frame here, reference frame, and you call it S prime, and so you can respond to this question. So you have two of these rays, okay, one is detected at time TA at location XA, okay. We are going to do it 1D. So we have X, okay. We have origin of our referential, and you have this one, this particle, okay. And so you will have at position XA, okay, you will measure, okay, with you have your clock here, you will measure, okay, this time TA. And a second, which will be here at XB, T, okay. They were there, okay. You detect them because they interact with your detector, okay. So the first muon interacted with this detector, okay. That's that position, that time, and the second, that position, that time, okay. What is the time interval between those two events in system S prime, which moves relative to S at speed? Okay, this is not actually, yes. At speed, so we have U, so you have another S prime, okay, and it is traveling at a velocity u along the x-axis, and we want to know if you have two detectors here, what will be the time interval between the two events, okay, in my system. So you will just apply the two almost 5 o'clock. I would like to, okay, so this is one example I can record, okay. After that, the solution you can try. This is an example of the tipler, okay. It's very simple. And so what you have x prime a will be gamma xa minus u t a, okay. and you have x prime b, which is equal to xb minus u t b. Okay, this is what you know. And also what you have, so you have here tb minus ta. Okay, once you know the transformation, the new transformation, the Lorentz transformation, all you have to do is remember that everything you write, okay, you have to say, you have to tell in what reference frame you are measuring it, okay, and be very careful with the notation, okay. And the other one you want to, okay, to determine here what is the time interval. This is t prime b minus t prime a, okay. So you can write here also TA, TB prime, or TA, if you want, TA equal TA minus ux over c square. Well, this is what we here, okay. You write t prime b gamma tb. Okay, these are the same events, okay, minus ux over c square, okay. And so you will have delta t prime, okay, which will be a function of ta minus tb, okay, you know it, but it will also be a function of, sorry, xa, xp, okay. It will also be a function of delta x, okay. So it's very simple application. I want to speak now about something important too. Okay, we can have a pause now, okay, because I will begin this one. So it's, I would say 10 minutes, okay, 10 minutes. And we come back in 10 minutes, okay?
Okay.
Okay. So the transformation we just studied, the Lorentz transformation, was for one event at position x time t. And now we will want to describe the movement, for example, of some particle, okay? And so this particle, this object P, we will say it has a velocity v in reference frame s, okay. And so I wrote down very clearly what it means to say, okay, that it is velocity v dop. Op is position of p in reference s, okay, and this is v, so this is 3d, okay. And so this same object has a velocity v prime in s prime, okay. Also what it means to say that these vectors, okay, these unitary vectors, they're the same. Vector doesn't have a position, okay. So essentially they are the same vectors, unitary vectors, okay. And we will, and s prime has a velocity u in s, okay. And so to simplify, we said that this velocity u is along the x-axis only, okay. This velocity doesn't have three components, okay. It is only along x, so this is very much simpler, okay. And so we can write it, okay. So this is very obvious. And so now what we are going to do is, okay, we know how to pass from, we are x, y, z, t, okay, and we know how to calculate, okay, positions coordinates and time in the other referential. Okay, this is Lorentz. But we would like to know now how do you pass from Vx, Vy, Vz, okay, to describe the velocity of this particle, okay, in another referential. Okay, so this is V prime Y, V prime C. Okay, so this is what we are trying to do now. So we are going to do it very, very carefully, because you see, this is wrong what I wrote here. Okay, I wrote dOp, which is the position over dt, and here I'll also write over dt, but it is dt prime. Okay, time is not the same, so this is over dt and this is over dt prime. Okay, so same thing here. Okay, no, here this, sorry, this is okay, this is in reference in frame S. Okay, but this is measured in S prime, so time is t prime. Okay, so I will calculate here V prime is d O prime P, okay, over dt prime. Okay, prime, I forgot to put it. Okay, so this is where you have to be very careful. You have position and time which depend on the, okay, so you write it down. So d x prime, you can write it as d of gamma x minus ut. T prime, dt prime, you can write it as d of gamma t minus ux over c square. Okay, so you can write it there. You want to determine this velocity as a function of your velocity. So you divide dx by dt. Okay, dx over dt minus u. So you will find this expression. Okay, using these two transformations that you already know. Okay, and so you do the same for v y prime. So you could say, okay, so I have y prime which is equal to y, and I have z prime which is equal to z, because the relative movement is along the x-axis. But as the fact is that you divide by dt prime, so it will depend on the velocity. Okay, so here you do the same thing, dy. Okay, dy prime equal to dy, same thing, but dt prime, you have to write it this way. Okay, and so you have your transformation of velocities. Okay, I hope I have written. Oh yeah, so you have the first one here, Vx prime as a function of Vx, Vy prime as a function of, actually it's Vx and, okay, Vx and, what is this V here? It should be Vx here, yeah? This is Vx. And so you have V prime as a function of, this is Vy, okay, over gamma 1 minus u Vx over c square. Okay, so this term here is in all the three components of velocity, not only on this one, which is in the direction of relative movement. Okay. Okay, so this is a limiting case. You know, u over c is this beta. Okay. In the case of classical physics, for example, Newton mechanics, okay, you have the velocities are very small, okay, if you compare it with the velocity of light. And so you can approximate, this is very small, okay? So you can approximate beta by 0, okay? And so you must find, okay, the classical transformation, yeah? Vx prime, Vx minus u, Vy prime, Vy, Vz prime, Vz, okay? If you do u over c here equal to 0, okay? So relativity is not different from classical mechanics, okay? Classical mechanics is a particular limiting case of relativity, okay? Because the velocity are so small, you don't need to compare it, okay, with the velocity of light, okay? And in general, the difference in time, okay? See, the time is the same because you see here, this is very small, okay? And gamma is also very t prime equal t. Gamma, I should show it, okay, actually, but you have to try. You can show for yourselves that t prime in the limit where this velocity is small, okay? If you compare it to c, you will have t prime equal t, and you will find, okay, the Galilean transformation, okay? And if you want to go from S prime to S, all you have to do is invert, okay, the velocity, the relative velocity. And so u now is minus u, so you have these expressions. So you have to be very careful when you do that. Let me see, we can do that. I think this is an interesting example. It's not only an application, it is the following, okay? This is an example of the Tipler, I think. And you have cosmic rays, and you suppose that two cosmic ray protons, cosmic ray is something, okay, in the cosmos, okay? So there are a lot of particles. We already see the muons, and this is proton, okay? And so we have two protons approaching Earth from opposite directions, as shown in the figure here. So you have Earth, we are here, and so you have the first proton this way, and the second proton this way, okay? And they have different velocities. So for example, v1, the velocity of this proton in as measured by on an observer on the Earth, okay, is 0.5.6 c, okay, and v2 is minus 0.8 c, okay. So you have this signal minus because we use okay, an oriented axis, okay. And so the question is, what is Earth's velocity relative to each proton? Okay, so I already answered it here, but if you don't look at it, you will say that this proton, the first proton, has velocity v1 in the reference frame of Earth, so the Earth should have a velocity minus v1 in the reference frame of proton 1, okay? And this is what happens. And the same holds for proton 2, okay? So this one is v1 is the speed. So I expect you, when you do some exercise, you solve some problems, okay, to write down very clearly what is the definition, what is the velocity you are using, okay? So you have to write this velocity, okay, is the speed or the velocity of blah, 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 relative to blah, blah, blah. It has to be very clear, and the signals are very important, so you have to, and I will say, if you write it, it will really help you solve the problems, okay? You only have to be very careful and to do everything with a lot of rigor, okay? So the first question is, you just invert, okay, the velocity. And the second one is more interesting, okay? What is the velocity of each proton relative to the other, okay? And so I can calculate the velocity of proton 1 in the reference frame of proton 2. Okay, so you see we have attached a reference frame S prime on proton 1 and S2 prime on proton 2. Okay, and so you have to, if you put things very, very clearly, so I say that S is reference frame of Earth, S prime reference frame of proton 1. Okay, so these are my two inertial reference frames. Okay, and so now I want to calculate, okay, I want to know what is the velocity of proton 2 as measured in the reference frame S prime. Okay, so V2, as I wrote here, V2 is the speed of proton 2 in S, and I will call V prime 2 the speed of proton 2 in S prime, okay? And so all I have to do is apply, okay, these transformations I have deduced before, okay? Being very careful with the sign and with the notation, okay? So V prime 2, which I want to calculate, okay? This is the velocity of the same particle in the other referential, which is V2, minus what is the velocity of the second referential in relation to the first. It's V1, okay? And so here you have, okay, remember you have Vx, V prime x equal Vx minus U over 1 minus U x over c squared, okay? What we just saw. So what is Vx? This is V2 minus V1. U is the velocity of S prime in S, okay? And so, same thing, U, and this is Vx, which is V2, okay? And so, after you have written this, okay, with the sign, you can write what is the value of V2. It's minus 0.8. Minus V1 minus 0.6, see, okay? So you write everything, and at the end you will find this one, okay? So you will find that the second proton, okay, has a velocity 0.9. I wrote a lot here, okay, 0.95 C, okay, as measured in the reference frame of the first proton, okay? If you had used the classical Galilean transformation, okay, what would you find? You would find, okay, you don't have this term here, and you would find that this second proton had a velocity 1 over, I said it was bigger, but it's obviously not true because this is the signal minus, okay? But you should have a relative velocity of 1.4 c, okay? And it's impossible, okay? Actually, we didn't see it yet, okay? But it is impossible. And I think we won't see it today because I won't have time. I will record a small video, okay, explaining it, that c is the biggest velocity you can, an object actually without mass can reach, okay? So classically, you see it would be minus 1.4 c, okay? But if you use the Lorentz, okay, transformation and the transformation, relativistic transformation on velocities, you will find it, okay? And if you calculate velocity of proton 1 relative to proton 2, you already can say it is plus 0.9459, or you can calculate and you, of course, will find the same thing, okay? So It's not difficult, but you have to be very, very careful. Okay. This one I won't do it. Okay. Okay. I forgot to put my. Okay. Just a minute. Okay. So coming back to a very important. Nothing new, actually. We already saw, okay, the relativity of time, of simultaneity, of space, everything. And so now, what I'm going to talk about is more almost vocabulary, but it's time dilation and length contraction, okay? So, let's say, the first one is, okay, time dilation. It's very easy to understand that you have the time intervals are different depending on the reference frame. We have seen that some two events that are simultaneous in one reference frame are not necessarily simultaneous in another one. So the smallest time interval is 0. They are simultaneous. And so the interval, the time interval will be different in other ones. Okay, so what will we see? There is something which is called the proper time. Okay, and we will see that in some specific reference frame we will have the smallest time interval. Okay, and we will have also the smallest length. Okay, for an object. Okay. First, let's start with the train. Okay, so you have your train. I will draw it. Your train is going at a velocity u. Okay, in relation to the platform. Okay, so this is S prime, and this is the platform. Okay, of the train. And so there is someone here inside, and there is a mirror. Okay, here. And so I will draw it bigger. Okay, so you have the mirror, which is horizontal. Okay, and you have your observer here. O prime is right here. Okay, and he will send some light signal toward the mirror. Okay, so the light will go this way, and it will go back this way. Okay, and so this observer will measure the time it took for the light to travel, okay, this distance. So we will call this distance L, for example, okay, and write it in black. L is the distance between the where the light was emitted and the mirror, okay, and so we will calculate delta prime because it's in S prime, okay. And so what is it? It is 2 times. It is the same time to go and same time to come back. And it is simply to the velocity of light is c. The distance is l. Okay. So this is 2l over c. Okay. So this is the time as measured. Okay. In S prime. Okay, so I will now design. Okay, draw what is this one as seen from the platform. Okay, so if you see it from the platform, it's not exactly an observer. Okay, because okay, let's see. First, you have the emission of light. Okay, the light will travel. It's not an infinite velocity, so it will Okay, the train is traveling, so the light will do that. I will put it in red. Okay, so this is the light. You have your mirror here. Okay, and so this is the first event. Okay, light is emitted, and the second event is light is detected back. It's not really beautiful, but it's okay. Okay, and so we want to know what is the interval. This is event 1, and this is event 2. Okay, and so we want to write delta t. Okay, so this will also be, it's not very obvious here, but this is 2 times, okay, the same. This is the same distance here. Okay, so this will be, what is the distance? Well, I don't remember where so what is this distance? You have a triangle. Okay, so what is this distance here? This is the distance the mirror traveled. Okay, so this is u delta t over 2. Okay, u is the velocity of the mirror in relation to the platform. Okay, this is also u delta t over 2. Okay, and you have here, what is this distance? This is L. Okay, in this direction is perpendicular to the movement, so you have y. Okay, y prime y, so L prime L. Okay, no problem. And so this is the same distance. Okay, so you have, I won't write it here, I will write that u delta t over 2, okay, square, plus L square equal this one square. Okay, and this one is c delta t over 2 square. Over 2 because it's 2 times. Okay, 1, 2. Okay, so you when you treat this triangle, it's only half the time. Okay, so you have, that's okay. I think there is no problem here. Okay, so what we want to solve this equation in delta t. Okay, so I'm writing here delta t. Okay, square. Okay, times, I can write delta t over 2 a delta t over 2 square times u square minus c square. Okay, it's better to do c square minus u square. Okay, c square minus u square. Okay, equal. Okay, so I have delta t equal, actually I will put it here and put it here. Okay, okay, and so I am going to write it in terms of 2L over C, or 2L over C times 1 over square root of 1 minus u square over c square. Okay, so this is very interesting because I can write the time delta t equal delta t prime time 1 over square root of 1 minus, this is beta, okay? Okay, so why is it interesting? Which one is the smallest one? Beta, always less or equal to 1, okay? So you will subtract from 1 something which is smaller, okay? And so you have, this is smaller than 1, this is bigger than 1, okay? So the smallest time here, okay, is this delta prime, okay? And it is called the proper time. And how do you know that this is the proper time? What is the difference between the way you measured this one and the way you measured this one? Look, here to measure the two events, okay, event 1 and event 2, okay, they occurred at the same place, and I could measure the two events with one clock, okay? So this is the same clock, but measured the time interval between these two events. Here, I needed two clocks, okay? I have my one clock here, one clock here. I needed two synchronized clocks to measure it. So what is called the proper time? This is the time, okay? The time interval, okay, in the reference frame where you can measure this interval time with one clock, okay? And so this is why we speak of dilation, time dilation. Why? Because in any other referential, okay, you have delta t bigger than delta than proper time, okay? So this is time dilation, okay?
Okay.
And so the other one, do I have time? Yes, maybe. Length contraction, okay? Length contraction. So this is the story you already watched. Movies, okay, where someone is traveling at a very high velocity. Of course, this is not a train, this is a special ship, and so on. And so when this person comes back, okay, he's so young, still so young, and his girlfriend is an old woman and things like that. So this is due to time dilation, okay? Because okay, we will speak in more details about it in a video, okay? Length contraction. You as well, you have something like, I will draw something like that. This is a bar, okay? So you have two extremities, A and B, okay? And I will call S, okay? Well, I will measure this actually in the referential S prime, which is the reference frame of the train, okay? And so this object of length L, okay, right. What is the length of this object, okay? You will have something here, you have your reference frame with, you don't need clock to measure it, okay? But you need the marks, okay, the special marks, and you will write that L prime, because it is in S prime, this is XB minus XA, okay? Okay? And you can write it this way because the object is still, okay, it is at rest in this referential. Okay, now you are this person, this is X point, okay, and you are here on the platform. And so how can you measure the width, the length of an object which is moving in relation with you? Okay, and so you will, when actually you will, the relative velocity is this way, u. Okay, so first you will, okay, you will have a clock, okay, and you will see when the first part here of the bar passes by you. Okay, you are here, O. Okay, and so you will have time, for example. Let me see. Does it have to?